report should be uploaded to Blackboard before class on Monday, and quiz 3 was supposed to be coming up next week, and I've made the decision that we're not going to have quiz 3. The reason being that for the first part, the electronic format of our class makes it difficult for us to do that in an efficient way. And then the other factor is that when we lost the instructional time, we just can't afford to miss out on the time for learning more about gradually varied flow. So no quiz 3. And then the last homework assignment of the semester, homework number 11, that's available now on Blackboard if you want to look at it. Homework 11 is going to be due before 11:59 on Friday the 24th, and so ordinarily assignments are due before class, but that one I'm going to give you some time after class as well, just in case on that last Friday class meeting we cover any additional examples or information that would help you with the homework assignment. Okay. So, are there any questions related to the announcements? Timothy's asking, will the lowest homework assignment still be dropped? The answer to that's yes. In fact, I can just take a look at the grade book real quick and see if it's doing that. That's a feature that I have to manually enable, so let me just see if that is active right now. Yes, it's already, the grade that you see already reflects the lowest grade being dropped. Okay, question about for the project, do we compile everything into one PDF or upload a zip folder? All right, what you should be submitting is a written report as well as a PDF file. Okay, so a PDF file of your written report, and if you're able to embed your PDF file of the network map into that same report, that's great. But the network map can be submitted separately, but it should be a PDF file of your network map. And then the water gems files I don't necessarily need to have. So you don't have to include the water gems files, but if I need to see yours, then I'll contact you if I have an issue, like if something in your map isn't clear. Michael asks about the calculations. I mean, that should be included as a scan in the appendix of your report. So any hand calculations that you've done, you should include. And basically, whatever I need to see to understand your work should be submitted. Okay, so we're going to talk about gradually varied flow today, and one part of that will be understanding the implication of this term wide channel. And so Manning's equation can be simplified if you have a really wide channel. And by wide, what we mean is that the width is at least more than 20 times the depth. And the reason why this is important, and the reason why this actually sometimes occurs, is a lot of rivers have a very large width compared to their depth. And what that allows us to do is, when there is a really wide channel, what's happening on the edges aren't quite so important. So for instance, if we had a trapezoidal side, then if it's really wide, like we're seeing here, the fact that it had just a little bit of flow extra on the sides of the trapezoid would be less important than if the channel wasn't wide. And so how that affects Manning's equation is that we can express Manning's equation in terms of the flow per unit width. And so remember, lowercase q is the flow that's occurring divided by the width of the channel B. And so it's really simple to find the flow depth using Manning's equation if you have a wide channel. If you have a wide channel, it's just the flow per unit width times the roughness divided by the channel slope to the 1/2 power, and then all of that to the 3/2 power. So just as an illustration of why this is valid, let's say, for example, that we had some channel that was 40 meters wide and the depth was 2 meters. Well, if you calculate the hydraulic radius for a channel that has a width of 40 meters and a depth of 2 meters, if we calculate the area and the wetted perimeter, you'd see that you calculate that and it's about 1.82. And that's relatively close to 2, which is significant because what we're assuming in this wide channel simplification is the hydraulic radius and the flow depth are approximately equal. Now, that's why we set the limit at it has to be at least 20 times wider than the depth, is because when you get narrower than that ratio, then it becomes less true that the hydraulic radius and the flow depth are equal. But the error introduced by implying the width of the channel width assumption is minimal as long as we keep the ratio to 20:1. So this is the modified Manning's equation for a wide channel, and similarly there's a modified equation that we can use for underflow gate equation. Now this is the underflow gate equation that we've looked at in the previous class meetings, and remember the parameters that go into that are a discharge coefficient having to do with energy loss, how high the gate is open, W, the water depth upstream, excuse me, sneezing is not a symptom of coronavirus, and finally the width of the channel, B. So the wide gate can be calculated, if you have a wide gate, that's again meaning that the width of the channel is more than 20 times the depth of the opening. We could find the flow per unit width using this function. So there's just kind of a similar idea that sometimes the gate is very wide. Now the bulk of what we're talking about today is gradually varied flow. RVF, rapidly varying flow, is what we were talking about with hydraulic jumps, and that's a dramatic, pretty interesting thing, but more often than seeing big rapid increases in flow depth because of the transition between super and subcritical flow, it's far more common for us to have situations where the flow is gradually varying. And so the picture that's shown on screen here is just a meandering river where in certain sections the width is narrower than others, and the width of the slope of the channel bed may be changing, and so all these variations in how wide the channel is and the slope of the channel, all those variations will cause corresponding changes in the flow depth. So there's all sorts of things that can cause it, like gates, weirs, dams, natural objects. Anytime we have non-uniform flow without a transition from super to subcritical, then we'll experience a gradual change. So as the depth changes, so does the velocity. And when we do our gradually varying flow assumptions, gradually varying flow equation, there's going to be a couple of assumptions that we'll have to employ. The fact that the pressure is changing in a hydrostatic manner as we go down through the channel. And another thing that is, well, let's look at first of all the causes for gradually varying flow, and then we'll talk more about the assumptions. And so water that's approaching an underflow gate will gradually vary, and you can see that the section where it's gradually varying here is as it gets closer to the gate. It's getting deeper because the gate has choked the flow. UF in this figure means uniform flow. So you'd calculate the depth with the Manning's equation during the uniform flow section, but then this choked flow causes pooling upstream of the gate. That it would be gradually getting deeper the closer you get to the gate. So another case would be as the water's approaching an overflow. You'd have a section where the flow conditions are uniform, and you could use Manning's equation to predict the flow there, but then as the water flows over the edge, that draws down the depth. And so that's another instance of gradually varying flow. Or if you have two different slopes, and the first slope wasn't steep enough to cause supercritical flow. So here, S naught, the channel slope at section 1, is still a mild channel. It's not hydraulically steep, meaning that it's not supercritical flow. Because if we had supercritical flow, then the transition wouldn't be gradual. There would be a hydraulic jump. But here, it's two mild slopes going together can cause gradually varying flow. Or if you have a steep slope and water's coming out from a gate, but it's just going to stay supercritical, so it would gradually increase the flow depth until it reaches the normal depth and we have uniform conditions, but the transition between the gate and the downstream uniform flow would be gradually varying. So those are some hydraulic features that could cause gradually varying flow, and what we want to be able to do is predict what is the depth, because we can't use Manning's equation. Manning's equation won't tell us what's the depth of the water in this region, and so we have to have some sort of a method that will allow us to start in the place where we know the flow depth is uniform, and then also the other bound will be where we have a gate or an overflow, some sort of a feature where we know its location and we know the depth at a fixed control point. What we're aiming to do is develop methods that will allow us to predict what's the flow depth everywhere else. So here's more about those assumptions. The methods that I'm going to teach you, the two methods that will predict what's the depth of flow when it's gradually changing, these two methods hinge on the assumption, first of all, that we're working with a prismatic channel. And early in the semester we talked about what that was. It just means that it's regular, and if you drew a center down the middle of it, it would have a mirror image. And so it's regular in shape. Steady flow, of course, means that the flow rate isn't changing over time. The gradually varied flow equation is applicable only when we have relatively small bed slopes. So we couldn't use it for water going down the spillway of a dam, but we can use it for any natural channel that we'll encounter. It assumes uniform velocity distribution, and I've talked about this one before, how it's a little bit weak, where we assume that even at the bottom of the river the velocity is going the same as at the top of the river. We had that same assumption when it came to the hydraulic jump equation, and I don't like it any more now than I did then, but it's kind of what we're limited to unless we want the math to get even more challenging, and you'll see it is with these assumptions. We use a kinetic energy correction factor of 1, which is applicable for the bulk of the conditions unless we had laminar flow, and we rarely will in open channel. We assume a hydrostatic pressure distribution, and then finally we're going to be applying this assuming that between the 2 points, upstream and downstream location that we're trying to interpolate the depths with this method, we're assuming that the n value doesn't change between those 2 points. So here's some theory that I hope will help you to understand the methods that we're going to use. Let's say that the water depth is getting deeper. So take a look. We've got a pretty steep channel slope here, and upstream we have depth y. Downstream it's deeper. We've got y plus dy. So this is non-uniform flow. But there's no hydraulic jump in between upstream and downstream. It didn't vary rapidly. It's a gradual variation in the flow depth. So this is gradually varying flow, and what we want to know is how can we predict what's the slope of the water surface, and how can we predict what's the new depth downstream going to be because of this. So if we look at the change in depth between upstream and downstream, then we can start with looking at specific energy. Specific energy, remember, is the flow depth and the velocity head. Well, the change of specific energy with respect to the change in depth can be calculated by 1 minus the Froude number squared. So 1 minus the Froude number squared, we don't have enough time to go into the full derivation of that, but it's just an application of how specific energy is changing with a change in flow depth. And the implication of it is that we can look at the 3 different slopes that are relevant here. The 3 different slopes are S sub f, which is the slope of the energy grade line, S naught, which is the slope of the bottom of the channel, and we want to know, we're trying to predict S sub w, so the slope of the water surface, because if we know the water surface slope, then that'll tell us if it's getting deeper downstream or shallower downstream, and also what's the rate of change in the flow depth. So we're going to substitute in, we're going to use the slope of the energy grade line for changes in the energy with respect to length, and we'll use the channel bed slope as a substitute for how the datum is changing with respect to this incremental length between the 2 points. The name of this equation that's just come up on screen, the dy dl, we call that the rate of variation of depth of flow with respect to distance along the flow direction. So you can see that's in quotes there because what this is saying is it's basically the slope of the water surface at a particular point. So if it is positive, then that means that the water is getting deeper in the direction of flow. If it's negative, then that means that the water is getting shallower in the direction of flow, so that the depth is decreasing. And we use this dy dl in order to predict what's the slope of the water surface at a given point. So S sub f we can determine from Manning's equation. S naught we can determine just from the given. S naught will usually be an input parameter of the problem statement. You could go out and survey that, or you could take the elevation at the bottom of the channel. That will be known. The Froude number can be determined by the flow conditions. And so if we know, for example, the critical depth and the flow depth at a given point, you can know the Froude number. And so we've got several equations that will define the Froude number for us. And so we'll be using this to calculate the water slope. And so if you combine the dy dl with the channel bottom, then that will tell you if the water slope is positive or negative, and whether the water is getting deeper downstream. So like I mentioned just a moment ago, the slope of the energy grade line is determined by Manning's equation. And so here's Manning's equation substituted into that equation, both in SI units and BG units. So if we solve Manning's equation for S sub f, and then substitute it in here, you can see it's in terms of the velocity, the Manning's n, which is roughness, and hydraulic radius. Now these equations are true for any section shape. It could be for a trapezoidal channel, a triangular, half circle, rectangular. This is always true, but we even have a simpler equation if it's a wide section. So if the channel is wide, hydraulically wide, meaning the width is 20 times greater than the depth, that's the threshold that we'll use for applying this, then we can predict the slope of the water surface relative to the bottom of the channel by knowing the channel bed slope and then the ratio of the normal depth to the flow depth at that location, and then the critical depth to the flow depth at that location. And so this will be a relatively simple equation for us to apply when the channel is wide. It's got kind of a funny name. If you go through the textbook, in a couple of spots, this equation is referred to as the process equation. And so, I don't know, I think that there was a reality star guy called the process, maybe. I don't remember. It was like, I don't watch a lot of reality TV, but if we were going to give this equation its reality TV name, it would be called the process equation. And if dy dl is positive, then that means that the water depth is increasing, and if dy dl is negative, then that means that the water depth is decreasing. So let's get a chance to practice this equation. We have a rectangular channel. We know the flow rate that's going through it is 20 cubic meters per second, and fortunately for us, this particular channel is hydraulically wide. 40 meters wide and 2 meters deep. So that means it's within this threshold of 20:1 width to depth, which means we can use the simpler equation for determining the process equation, and we can also use this simple equation for normal depth. So with the given bed slope and the roughness value that's known, let's first of all find out what is dy dl. And we want to know what is dy dl at a particular location where the flow depth right now at this spot of interest is 2 meters. Now just to clarify, the normal depth is not 2 meters. This is a certain spot where either there's pooling because of an obstruction or the flow is going over a drop-off and the flow is decreasing, but for whatever reason it's not flowing at its normal depth, it's flowing at some other depth. So what we're going to do is, first of all, you find the flow per unit width, Q, lowercase q, then substitute that into the critical depth equation, find the normal depth, and substitute both of those here into the process equation, along with the given bed slope. So find dy dl at the location where the depth is 2 meters, and then from its sign, whether it's positive or negative, that will tell us whether the depth is getting deeper or whether it's getting shallower in the direction of flow. And then finally, we can substitute the given slope and the process equation into this formula for S sub W. So I'll pause the recording, I'll stop talking for a few minutes and give you a chance to dust off your calculator and start substituting these values into the flow per unit width, critical depth, normal depth, and dy dl. Okay, let's take a look at those numbers so far. We started off with needing to calculate the flow per unit width. So if it's 20 cubic meters per second going through a channel that's 40 meters wide, then that gives us a flow per unit width of 0.5 meters squared per second. And we can use that to calculate the critical depth. Now remember, this critical depth equation only applies if a channel is rectangular. If the channel isn't rectangular, then we would need to determine the critical depth by setting the Froude number equal to 1 and then solving for y sub c there in the area formula. So we have yc, and then we can use this normal depth equation, which again we have to keep in mind, this normal depth equation, this new one that I'm showing you here, is only valid if the channel is not only rectangular, but it also has to be hydraulically wide. So that's even more restrictive than the critical depth equation, because the critical depth equation is valid just as long as it's rectangular. So this one can only be used if it's rectangular and, well, if it's hydraulically wide. It doesn't have to be rectangular, but hydraulically wide, which is effectively rectangular. Okay, so our normal depth 0.912 meters. All right, now when we substitute all of that into the process equation, I just remembered the name of that reality guy. His name is The Situation. So, anyways, this is the process equation. So you substitute in the channel slope, the ratio of the normal depth to the flow depth at that location, the ratio of the critical depth to the flow depth at that location. The dy/dl is 1.39 times 10 to the minus fourth. Now since that's positive, then that means it's getting deeper in the direction of flow. Any questions so far about the dy/dl calculation? Okay, so the interpretation of that being positive is that the flow depth is increasing in the direction of flow. Now this dy/dl though is just relative to the channel bed, so we're going to subtract out the slope of the channel in just a moment, but what I'm drawing here is I'm drawing a sketch of, this is a location where we know the actual flow depth is 2 meters and the normal depth is less than that, and then the critical depth is less than the normal depth. So comparing the normal and the critical depth is one way for us to diagnose whether the conditions are supercritical or subcritical. And anytime the normal depth is greater than the critical depth, and that tells you that you've got a mild slope. And so in our case, this is a mild slope, and we have subcritical conditions because the flow depth is greater than the critical depth. All right, so the water surface slope, we substitute in the channel slope in negative terms because the water is flowing downhill. We have to have like an absolute understanding of what slopes are when we are doing this gradually varying flow stuff. So the S0 is negative, but the dy/dl is positive, and so then the net difference between them is that the water surface slope is negative 1.1 times 10 to the minus fifth. So that means that relative to the horizontal, the water surface slope is decreasing. So the water is getting deeper, but the slope is even steeper than that. And so the net effect is that overflow in the direction of flow, it wouldn't be flowing from left to right if it wasn't going downhill, and it is. Okay. So we used the new Manning's equation that you've learned for a wide channel. We substituted into the process equation, and then the interpretation that we were able to get from that is whether the flow depth was getting deeper or shallower in the direction of flow, and in this case it was getting deeper. Alright, so here's the process equation, and the three depths that we can use to classify water surface profiles are the normal depth, the critical depth, and the actual flow depth, just like in that sketch that I showed you from our example. We compare those three depths and then we can draw conclusions from them. And we can use those depths to classify what caused the gradually varying flow and how it might be changing in the direction of flow. So, for instance, just looking at the slopes, there are different categories, like if the slope is less than the critical slope, then this is a mild channel. If the and you notice it's a mild channel, the way that you know that is because the normal depth is bigger than the critical depth. That's how you diagnose that you have a mild channel. But you diagnose a steep channel if the critical depth is greater than the normal depth. And then if the two are equal to each other, that's an indication of a critical slope. Horizontal slope just means that it's flat and that there isn't a normal depth that can be calculated if the slope is flat. And then an adverse slope means that water is flowing uphill. And it can do that just for a little while, not for very long, but if you have enough velocity, water can flow uphill temporarily. I've actually been on a water slide that goes uphill temporarily. It's pretty cool. What we do to diagnose the flow regime in open channel flow is first of all start with comparing the normal depth and the critical depth, and then that tells you if your water surface profile is M, S, C, and so the slope is given the abbreviation with these cases. And then next, you classify the actual observed flow depth as whether it's in one of three flow zones. We call zone 1 to be any flow depth that's greater than the normal or critical depth. Zone 2 is when it's between them, and then zone 3 is when it's beneath both of them. Now, whether, which one's on top, like whether it's the critical depth or the normal depth on top, that goes back to the previous slide, where the one on top is going to be the normal depth if it's a mild flow, and it's going to be the critical depth if flow is steep. So just the actual observed flow depth should be either above both of them, in between the two, or beneath both of them. So those are the three different zones. And so remember the dy dl, if it's positive, then that means that the flow depth is increasing. If it's negative, that means the flow depth is decreasing. And so the next thing that we want to look at is whether it's mild versus versus steep, and whether you're in zone 1, 2, or 3 is going to tell you how the flow depth is changing. So let's look at, just for instance, a mild slope. If you have a mild slope and the water depth is in zone 1, then that means it's getting deeper in the direction of flow. So this sketch just tells you that if you have an M1 profile, then the water depth is increasing in the direction of flow. But if you have an M2 profile, that means you've got a mild slope, but for whatever reason the flow depth is getting shallower downstream. And so that could occur if the water is flowing over the edge. That's what could cause the drawdown. And then an M3 profile would be that you have a mild slope, but for some reason the flow depth is less than the critical depth. And so something that would cause that is flow from an underflow gate. When it's about to go up to a hydraulic jump, we still have gradually varying flow until it goes through the hydraulic jump. The same thing we can do with steep profiles. We can know that in every case, if the water depth is in zone 1, then that means it's going to be getting deeper in the direction of flow, and we can look at the different zones to predict how the water depth is changing in the direction of flow. So your textbook has sketches similar to these for critical, horizontal, and even adverse. There aren't adverse zone 1 or horizontal zone 1 because we don't have the normal depth, and so the zones are distinguished only by the critical depth. If the flow isn't going downhill, you can't calculate a normal depth for that. Just some more sketches showing the hydraulic features that can cause M1, M2, and M3 profiles. So you can see the M1 is water pooling as it approaches some obstacle. That's what would cause an M1 profile. An M2 profile caused by flow over the edge. An M3 profile caused by supercritical flow. And likewise, if you have a steep slope, there are different hydraulic features that would induce flow in the 1, 2, or 3 zones. And different things that would cause, for example, flow on an adverse slope. Water could be getting enough velocity from an underflow gate that you've got enough velocity now that the water has the energy needed to go uphill temporarily, and then it's flowing over some downhill. So it would be gradually varying as it approaches the hydraulic jump, rapidly varying through the hydraulic jump, and then again gradually varying as it approaches the drop-off. And then yet here's another third textbook's way to kind of summarize and make it clear how you diagnose the flow regime, whether you have mild, steep conditions, and then which zone you're in. And then the effect of that is whether the water depth is increasing or decreasing in the direction of flow. Okay, So let's go through the example of, for this particular situation that's summarized, try to calculate how the flow is changing. We know the channel width is 8.5 meters. The given depth at just this location, this is one particular point of interest, the depth is 3.2 meters. And so the normal depth is going to be different from that. And we also need to calculate the critical depth because we're going to compare the critical and the normal depth to find out whether we have a mild or steep slope. And then we're going to compare this given depth to find out whether we're in zone 1, 2, or 3. So we'll classify the water surface profile. So what you should do is use the equation for critical flow to find the critical depth here with the flow per unit width. Now this isn't hydraulically wide, so just to speed things up, since we've got limited time, I'll tell you the normal depth. Let me pull that up. Okay, so you calculate the critical depth right now. And you calculate the critical depth, and I'll tell you that the normal depth is 2.7 meters. Okay, when somebody has the critical depth, will you please type it into the chat tool or enable your microphone and tell us what is the critical depth here. Okay, so Jeffrey has told us that the critical depth is 1.1 meters. Okay, he solved for critical depth, so 1.1 meters. So what we have is, I said the normal depth is 2.7 and the critical depth is 1.1. So normal depth 2.7, critical depth 1.1. That means we have a mild slope. So we have an M profile because the normal depth is bigger than the critical depth. And now, are we in zone 1, 2, or 3? Well, since we have this given flow depth is 3.2, that's greater than either the critical or the normal depth. So that means we are in zone 1. So if I just bring that solution up on the screen here, you can see that I went through the process of calculating the normal depth using Manning's equation, and I didn't use the abbreviated version of it because this is not a wide channel. So we got the normal depth, here's the critical depth, and since the flow depth of 3.2 meters is greater than either of those, then that's what makes it an M1 profile. So that's how you can diagnose what is the water surface profile. Now the second part of this, find the water surface slope. We can find the S sub F with the slope of the energy grade line. So rearranging the Manning's equation for the slope of the energy grade line, and then putting in the N value that we know, the flow rate, the width of the channel, the flow depth, all of the parameters for this channel tells us that the slope of the energy grade line, S sub F, is 0.000634. So that is S naught, and then we subtract out, that's S sub F. The S naught is given directly. So we use Manning's equation to find S sub F. We also are going to need the Froude number squared because in this equation is, in the denominator, is Froude number squared. So the slope of the water surface is 0.000382. So it's getting deeper in the direction of flow. which is consistent with what we know about an M1 profile. Earlier we'd calculated that this is an M1 profile just on the basis of comparing the flow depth to the normal depth and the critical depth. And so an M1 profile, this sketch that's off to the side tells us it should be getting deeper in the direction of flow. And then when we calculated dy dl, that tells us the rate that it's getting deeper. It's getting deeper at a rate of 0.000382. So that's the change of depth. Dy dx is just telling you how much deeper it's getting in the direction of flow. So for every 1 meter horizontal, it's getting deeper. I guess that's what, 0.3 millimeters. Yeah, 0.3 millimeters of additional depth for each meter of flow direction in the horizontal distance. All right, so that's how we calculated the slope of the water surface. Okay, well, that's all the time we have for today. I kept you a little bit late last time, so I promised to give you back those extra minutes this time, and I'm going to make it happen. Let's just look at the applicable announcements here to remind ourselves that the project report is due on Monday. We're not having quiz 3 on Monday, but what you can do after submitting your project report is start working on homework 11, and you'll have until 1 minute before midnight to submit that on Friday the 24th. Any questions before we finish for today? All right, well, if not, I hope you have a great weekend.